it to him. Huh, what's this? My brother's equations. What a geek. I wonder if I can use these to get the car for my father.
Hello, Avery.
Can I have the car? I learned about response time with these equations right here.
Just because you have equations doesn't make you a good driver. What happens when you actually have to apply them on the road in a dangerous situation?
Well, I know that when you get older, your response time slows down.
Yes, but just because you're older doesn't mean your response time isn't just as good as yours.
You want to test your response time?
Of course.
Hey! Boy! Get back here now!
This just in, a 15-year-old boy named Chris Avery allegedly took the keys from his parents and tried to drive away with the car. Unfortunately, he put the car into reverse instead of drive, sustaining maximum damage to his parents' garage. This story and more at 9.
Huh?
This is Connor. Connor is busy working away on his physics homework. But little does he know that physics is working on Connor as well.
Well.
You see, Connor is in motion, which is and to figure out his exact momentum, you would figure it out by times his mass by his velocity. So, let's hypothesize that Connor weighs 75 kilograms and he's going 2 meters per second. Then his momentum would be 150. And because he is in motion, he also has inertia. Inertia is one of Newton's laws, stating that a body in motion tends to stay in motion, which Connor is still in motion unless an outside force acts upon him. However, Connor is moving in a circular motion. This is also part of one of Newton's laws. The body in motion will tend to stay in motion in a straight line. You see, it is unnatural for Connor to be moving in a circular motion. The force causing him to move in this direction is, well, the spinning chair. Now, if an outside force was to stop the circular motion, Connor's body would want to keep moving in a straight line once the circular motion was stopped. Hypothetically, let's say someone's foot stopped the chair. Ah, yes. Yet another great observation of physics.
Ow, Hannah, stop poking me. Ow.
Are you reading the Bible?
No, I'm looking at it and thinking of what it would be like if I actually read the Bible.
That's really stupid. Does this hurt?
Stop poking
Does
me.
this hurt? Why is your hair all fluffy and
Ow.
crazy? No! I want to poke you.
Cut.
Ow!
Oh, what up now?
That really hurt, Connor.
Well, you poking me hurts even more.
No,
You know what? Because pressure, homie. Alright, pressure is force divided by area. So anyways, my pressure, if I weigh 150 pounds and my foot is 44 square inches, is only 3.4. When yours is 80. Because you're putting 5 pounds of pressure on me, and the area of your pencil tip is 1/16 of an inch. That's 80 pounds. Hurts, girl. Ow. Look at this. Look at this. Hannah's pressure is greater than Connor's pressure.
Connor, you're a freak.
Ow.
Hello, everybody. I am a drunken businessman coming home from work.
So, this is Bobby Schwartz. He was drinking Welch's grape juice, so his reaction time will be tripled since he's so much impaired that he can't think for himself. Let's see what happens, kids.
Aha! So, kids, before we can see if Bobby can make that intersection, we have to see the physics behind it. We have to see his stop zone and his go zone. Stop zone is velocity times the reaction time, plus velocity squared over 2 times the deceleration rate. And the go zone is velocity times the yellow light time minus the intersection length. So in this case, Bobby's stop zone would be 180 meters and his go zone would be 110 meters.
So when you subtract the go zone from the stop zone, you get 70, which is a dilemma zone. It's a gap in between the two. So if he was in the dilemma zone, he'd be screwed. He couldn't stop or go, and he'd get rammed by an oncoming car in the intersection. Ow! Now let's see what happens. See, Bob in the dilemma zone couldn't run the yellow light because it actually turned into a red light, and he got rammed by Bugs Bunny. Sorry. Hello, kids. Well, a common fallacy in the thought process of the young physicist is centripetal and centrifugal forces are the same thing. And usually people mispronounce it and call it centrifugal force. What's up with that? It doesn't exist. But anyway, they're complete opposites. Centripetal force is a pull force when taking a turn. I'll explain more of that. And centrifugal force is a push force when taking a turn. And it's not a real force, it's called a pseudo force. And it's not real like Santa Claus. There you go. But anyway, more about centripetal force. You'll feel it in a banked turn when you're taking a sharp turn. It's sort of an inward force, and it actually exists. But why centrifugal force is not real is because, well, the law of inertia states that a body in motion wants to remain in motion in a straight line until acted upon by an outside force. So anyway, with your curved path, basically your body wants to go something like this. But that's all those straight lines and stuff. So it tries to move like that, but you're feeling the angular acceleration in all of those directions, and that's what you're feeling is the acceleration of you changing directions in those directions anyways. So scientists illustrate this with the formula mass times velocity squared divided by the radius. So the smaller the turn, the sharper the turn, the smaller the radius is going to be, and the more centrifugal force you'll feel. Now, I'll give a demonstration of centrifugal force using this little guy, Edgar. Come hither. Alright. So watch him take this turn. With a 2-foot turn radius, anyway. He's gonna go straight. Oh! Wonder why he just fell out of the car, though? Let's see. Because he's not going in a straight line, obviously. But his centrifugal force would be 9, because he weighs 2 kilograms with the car, and he's going 3 miles an hour with a turn radius of 2 feet. So, if I drew this out, this is his sort of motion, but he wants to go like this, which is completely impossible. So every time he changes directions, his momentum is going in these ways. So he's feeling the force of him accelerating at an angle. Angular acceleration.
Hello, kids. Let's discuss what happens when centripetal force is applied to Poe in the car. Come here, there. Come. Now, when we have Poe in this car, he would like to go in a straight line, because a straight line is natural, and we all want to go in a straight line. However, when I am acting on the car that Poe is in, I am applying centripetal force to the car. Because centripetal force is the force that is causing Poe to go around in a circle. Now, if I were to so much as cut the centripetal force holding him in a circle, like so, he would go in a straight line that way, because a straight line is natural, and a circular motion is not. And a circular motion is the cause of a centripetal force being acted on by the car, thus being me.